Is time really real? Or is all this everything we feel, measure, calculate just an illusion? Something conjured up by our minds by consciousness, or perhaps by the laws of physics as we happen to understand them today. I've been thinking about time again, particularly about, well, how Einstein sort of shattered the whole idea that it's fixed, you know? Because for centuries we assumed that time was this absolute thing. This universal clock ticking away the same everywhere like a stage, really the stage on which the universe plays out. But then Einstein comes along early 20th century and says, no, it's not like that. Time is its relative. It depends. It depends on how fast you're moving. And also on where you are in a gravitational field, and that's not just philosophical, it's measurable, it's physics. So in Special Relativity, which he published in 1905, Einstein proposes that the speed of light is constant for all observers. That's the foundation. That's where it starts. And once you accept that everything else changes, because if the speed of light is fixed, then time itself has to stretch or shrink depending on your frame of reference. That's time dilation. That's one of those things that sounds abstract at first, but it's real. It happens. We've measured it. It's not just an idea. Now, what does that mean exactly? Well, imagine two observers, one sitting still, let's say, and the other moving very fast. Not just fast, but near the speed of light. From the perspective of the person sitting still, the clock of the one who's moving ticks more slowly. So if you're the one flying in a spaceship, zipping along at close to light speed, your experience of time slows down. It slows down compared to the person you left behind. And that's not an illusion. It's not just something that happens in your mind. It's a physical effect. It's been tested with extremely accurate clocks, atomic clocks, flying around the Earth on satellites, and they tick at a different rate depending on their motion and their altitude. That's the thing. So it's not science fiction. It's everyday life now, especially in technologies like GPS. GPS, for example, it wouldn't work properly without accounting for time dilation. The satellites are moving fast relative to us here on Earth, and they're also further from the Earth's surface, so gravity is weaker up there. That means two things are happening at once. Because of special relativity, their clocks tick more slowly because they're moving. But because of general relativity, which Einstein published 10 years later in 1915, the clocks actually tick faster due to the weaker gravitational field. So yes, both effects are at play. You have to account for both. If you don't, GPS signals go out of sync and you're lost. Literally lost. And this brings us to gravity. That's where general relativity comes in. And this is the real twist, I think. Because in that theory, gravity isn't really a force in the old Newtonian sense. It's the curvature of space-time itself. So massive objects like stars or planets or black holes, they bend the fabric of space-time, and that curvature affects how time flows. It's a beautiful idea, actually, that time itself bends, slows down. Near something massive, time passes more slowly. You can see this dramatically near a black hole. There's a famous example. The film Interstellar actually got it quite right in a scientific sense. There's a scene where the characters land on a planet orbiting very close to a black hole, and due to the immense gravity, time for them ticks much more slowly than for someone who remains further away. So when they return, hours later for them, decades have passed for the person who waited. And that's based on real physics. The numbers were adjusted for dramatic effect, of course, but the underlying concept, that's Einstein's prediction. The closer you are to a massive object, the slower your clock runs. And again, this isn't metaphorical. It's not perception. It's measurable. We've done the experiment. Atomic clocks flown to different altitudes on mountains or on aircraft run at different rates than clocks at sea level. Just a tiny difference, but it's there. The stronger the gravitational field, the slower time moves. So in a very real sense, you age more slowly on the ground floor of a building than you do on the top floor. It's an incredibly small effect, yes, but measurable. Now, there's this wonderful thought experiment. It's often called the twin paradox. Yes, it's simple, but very revealing. Imagine two twins. One of them stays on Earth, the other goes off on a spaceship traveling close to the speed of light and then returns. According to special relativity, the one on the spaceship will have aged less, significantly less, depending on how fast they went and how long they were gone. That's the paradox. Not because there's any contradiction in the physics, there isn't, but because it challenges our intuition. We expect time to flow the same for everyone everywhere, but it doesn't. That's the reality. And what's striking, I think, is that we have to change our language when we talk about events in the universe. We can't just say this happened at this time as if everyone would agree, because simultaneity itself, what it means for two things to happen at the same time, is also relative. If two lightning bolts strike at either end of a train, say whether they appear simultaneous depends on your frame of reference. Someone on the platform might say yes, they happened at the same time, but someone on the train might disagree. And both are correct within their own frames. That's the genius of the theory. It doesn't tell you what's really happening. It tells you how reality appears to observers in motion. So time becomes it becomes entangled with space. That's the key idea. Space and time aren't separate things. They're part of a single structure, space-time. And the intervals between events in this structure depend on the observer. It's the space-time interval that remains constant, not the distances or the time separately. And once you get that, it changes everything. Because if time is not universal, then reality itself becomes layered, observer-dependent. And that's hard to accept because we live in a very Newtonian world, right? We walk around assuming that 1 second for me is 1 second for you. And well, mostly that works. But on cosmic scales or high speeds or strong gravity, it doesn't. It's funny because time feels so personal, so deeply intuitive. We wake up, we live, we sleep, we experience moments flowing one after another. But the physics says that flow is a kind of illusion. Time doesn't flow, it just is. Events exist in space-time like locations on a map, and our consciousness moves through them. Maybe that motion is just something we impose. But in the equations, in the mathematics of relativity, there's no special now. There's no universal present. There's just events. And the order of those events, their timing depends on how you move and where you are. I think that's the most astonishing thing about it. That something so basic, so foundational to our experience, turns out to be relative, not fixed, not universal, and yet reliable, predictable. You can build a satellite system, send a probe to another planet, navigate a spaceship through the solar system, and it works. Because the equations are right, they describe a world that's deeper than our intuition. A world where clocks tick at different rates depending on how they move and how deeply they sit in a gravitational well. So when we talk about time being relative, it's not just a curious side note. It's fundamental. It's woven into the structure of the universe. It means the future isn't something that's simply waiting to happen. It means that each of us in our own small way experiences a different version of reality stretched and curved by motion and mass. It means, in the words of Einstein himself, that the distinction between past, present, and future is only a stubbornly persistent illusion. And yet somehow that illusion is what allows us to live. There's something quite strange, something deeply strange, I think, about how we perceive time, because it's not just clocks and physics and equations, is it? No, it's emotional. It's something that moves through us. Or maybe we move through it, I don't know. But what's really clear, is that the time we feel is often wildly different from the time measured by, say, an atomic clock. That's the bit that fascinates me. the idea that there are, in a way, two kinds of time. There's physical time, the one that Einstein reshaped for us, and then there's psychological time, the time in our heads. And that one, well, that one bends and stretches in ways that have nothing to do with motion or gravity. So, for example, have you ever noticed how time seems to slow down when you're anxious? Or how it drags when you're bored? You're sitting in a waiting room, no phone, nothing to read, just silence. And a minute feels like 10, but then when you're engaged, when you're immersed in something fully in it, hours pass, and it feels like nothing. It's as if your mind isn't measuring time in seconds or minutes at all, but in experience, in novelty. And that means, well, it suggests that time, at least internally, isn't ticking at a steady rate. It's something else, something constructed. Now that's not just a poetic observation. There's research, real research in neuroscience and psychology that supports it. What seems to happen is that our brain uses attention as a kind of internal clock, or maybe more like a metronome. Yes, a metronome that ticks faster when we're alert and slows down when we're not. So when you're highly anxious, say during a stressful moment, your attention sharpens, right? You notice more. Your brain processes more data, and because it's processing more, it creates more mental snapshots. So when you look back on that moment, it feels like it took longer, like time expanded. On the other hand, when you're relaxed or disengaged, your brain does less of that. It compresses the moment, so it feels shorter in retrospect. It's not about the clock. It's about the density of experience. That's the phrase I heard someone use once, the density of experience. And I like that because it's not about what's happening in the world. It's about how much of it you're taking in, how much you're aware of. And children seem to feel time very differently from adults. When you're young, everything is new. Every day, you're learning something, tying your shoes, reading words, discovering how gravity pulls the apple off the tree, and that novelty, that constant stimulation. It creates this sense of endlessness. Childhood summers feel like they lasted forever. But then as you get older, your days become more routine. You drive the same route, go to the same places, do the same things, and because of that, your brain kind of compresses the memories. So when you look back, entire years can seem like they passed in a blink. That's a bit unsettling, really, that your perception of time speed depends on how interesting your life is. And there's another layer to it, trauma. In moments of trauma or danger, people often describe time as slowing down dramatically. There's that classic description, the car crash that feels like it took minutes, even though it was over in seconds. And neuroscientists think that what's happening is, again, the brain is firing more rapidly, taking in more data. Your amygdala, that little almond-shaped part of the brain that processes fear, becomes hyperactive. So your mind creates more impressions per unit of external time, and that overload, that intensity, stretches the moment. So subjectively, it feels longer. And yet it's not just high-stress situations that affect our time sense. Meditation does the opposite. People who meditate regularly often report that time slows down for them. Not in a frantic, anxious way, but in a kind of expanded calm. It's as though the act of observing your breath or your thoughts or the silence itself creates more space between moments. You begin to notice the time within time, the micro moments, and that feels slower but also deeper, fuller. And dreams. Dreams are another mystery because dreams unfold in a kind of elastic time. You might wake from a dream that felt like it lasted an hour only to find that you'd been asleep for 5 minutes. Or the opposite, you dream a flash and hours have passed. There's no reliable clock in the dream world. And yet we often come back with the memory of a sequence, a before, a during, an after. So the brain constructs time even in the absence of time. It builds a narrative. It weaves events into an order. And that order, that structure, that's what we call time, psychologically speaking. It's remarkable, isn't it, that the mind needs time to think. Even the simplest sentence, "I went to the store," implies a sequence, a movement through time, Language is built on it. Memories anchored in it. Without the concept of a before and an after, there's no narrative. There's no identity. Because identity, in a way, is the story you tell yourself about yourself. And that story unfolds in time. You are who you are, not just because of what you are now, but because of where you were and what you might become. And there's something quite beautiful, I think, in the way we stretch time and memory. Because when we remember something vividly, when we recall a holiday or a moment of love or grief, it's not just a picture, is it? It's a sense of duration. You remember not just what happened, but how long it felt. And that means we're not just remembering events. We're remembering time itself, our experience of it, that internal rhythm. But then there's this strange duality, because while we can stretch and compress our sense of time, we can't stop it, not even internally. We can distort it, but we can't freeze it. There's always a now and a now after that. Consciousness seems to require it, this continual unfolding, this progression. Some philosophers have even argued that time isn't something that exists out there. It's something that emerges from consciousness itself. That without a mind to observe it, there's no flow, no distinction between one moment and the next. And maybe that's why time can feel so heavy when we're depressed. Because time doesn't just pass, it presses. It weighs on you. The future becomes a burden, the present an endless now. And the past, well, the past becomes something you can't escape. So again, it's not just the ticking of a clock. It's the emotional gravity of time, the way we carry it. And when we're in love, well, then it's different again, isn't it? Because time in love is elastic too. Moments become golden, fleeting, but eternal. A glance can last forever. And yet the hours vanish in an instant. And that to me is one of the great mysteries, that time is not one thing. It's many. It's a landscape we move through, but also something we construct as we go. Like a road that only appears beneath your feet as you walk. And think about aging, not biologically, but psychologically. Because there's evidence that our perception of time accelerates as we get older. Not just because of routine, but because each year becomes a smaller proportion of your life. To a 5-year-old, a year is 20% of their existence. To a 50-year-old, it's just 2%. So it feels faster, like the pages of a book flipping quicker near the end. And that's why people sometimes say, life speeds up. But perhaps what's really happening is that our minds adapt. They compress. They summarize. They create highlight reels instead of full recordings. And those reels, those edited versions of reality, are what we call memory. So our past becomes this stitched-together sequence of moments with time smeared unevenly across it like paint. Thick in some places, thin in others. It's a strange thing. We measure time with extraordinary precision. We can split seconds into billions. But inside it's all so subjective, so unpredictable. And maybe that's what makes it so human, that our minds turn time into meaning. That we can feel the difference between a minute of silence and a minute of music, even though the clock says they're the same. Because inside they're not. They're worlds apart. Maybe that's what time really is. Not the ticking of the second hand, but the story we tell ourselves between each tick. Something went wrong while generating the response. If this issue persists, please contact us through our help center at help.openai.com. There's a very strange idea in physics that's been gathering attention for a while now. It's not mainstream exactly, not yet, but it's serious. It's the idea that time isn't fundamental, that it's not really built into the foundations of the universe, that instead it emerges like temperature, right? So temperature isn't a fundamental thing in physics. It's something that comes from the movement of atoms, a property of many things acting together. And some physicists are now saying, well, what if time is like that? What if it's not something that exists on its own deep down, but only appears when you zoom out? Now, it's a really unsettling idea, actually, because time feels so basic. It feels like the thing that everything else happens in. And yet, if you go right down to the quantum level on the equations, the ones we use to describe the fundamental particles don't necessarily need time at all. Not in the way we experience it. They're just relationships. States changing into other states, but not always with a ticking clock. And there's this idea, particularly in certain versions of quantum gravity, that space-time itself might be built from something even deeper, something more abstract. And if that's true, then maybe time is just a convenient illusion, a useful approximation. It's like how water seems continuous and smooth, but when you zoom in far enough, it's just molecules, right? Just hydrogen and oxygen bouncing around. And if space-time is like that, if it's made from something more granular, then maybe time isn't a river flowing, but a kind of pattern emerging from the interactions of deeper things we can't see. There's a name that comes up a lot in this context. Carlo Relli. He's done a lot of work in a field called loop quantum gravity, which is one of the approaches to combining quantum mechanics with general relativity. And in that framework, something fascinating happens. Time kind of disappears. It's not in the fundamental equations. What you get instead are relationships, structures, things interacting, but no global clock, no universal time. And that's not just a mathematical curiosity. It means that at the deepest level, the universe might be timeless. That before anything like a clock can tick, before any notion of past and future can arise, you need complexity. You need systems, observers perhaps, entanglements. And time then becomes a property of how these things relate to each other. It's not a backdrop, it's a consequence. There's another framework called the Page-Wouters mechanism, and it's hard to explain, but the basic idea is that you can model a universe with no time in its fundamental laws. But where time emerges relationally, that is if you take part of the system and treat it as a kind of clock, then relative to that clock, the rest of the system does seem to evolve. So time in that view is about correlation. It's about comparing things. One thing changes and we notice another thing changing with it. That's time. But the whole system taken as a whole doesn't change. It just is. And that raises a very deep question, doesn't it? If the total universe is static, frozen, and we only experience change because we're inside it, moving from one part of the structure to another, then what is time really? Is it a journey through something fixed, or is it a trick of perspective? Now, there's another piece of this puzzle that comes from thermodynamics, specifically from entropy. And we've already talked about the arrow of time being connected to entropy increasing, but there's more. Because in quantum mechanics, there's this notion that the fundamental processes are reversible. You can run the equations forward or backward. There's nothing in the core rules that says time has to flow in one direction. And yet in our world, we only ever see the coffee spill, not unspill, right? The vase breaks and it doesn't reassemble. That's because of entropy. It's not a rule about time. It's a rule about probability. So if time at the fundamental level is reversible, but we experience it as one way, then that might mean our experience of time is tied not to fundamental laws, but to information, to knowledge. And there's a line of thought, more than one actually, that says time emerges from the way information spreads, that it's about entanglement, quantum entanglement, and the way parts of the universe become correlated. There's a paper I read, I can't remember who wrote it now, but the idea was that time could emerge from quantum entanglement patterns across a network of states, like a web. So instead of time being a thing that flows, it's more like a tapestry. You pull on one thread and the others shift in response. And that shifting, that updating of information, is what we interpret as time passing. But really it's just the system adjusting. And if that's right, then time might not be the same everywhere. Not just because of relativity, but because of the structure of entanglement, the way different parts of the universe are connected. And that could explain some very weird phenomena. There's even talk, though it's still speculative, about time being an emergent direction in Hilbert space. Now, Hilbert space is the abstract mathematical space where quantum states live. is vast, infinite dimensional. And if you can define a direction in that space, a direction in which entropy increases, then that could be your time, not in space-time, but in state-space. And this is where it gets properly weird, because it suggests that there could be systems where time flows in a different direction, or not at all. That time might be local, not global. That there might be regions of the universe, maybe tiny, maybe vast, where the sequence of events, the before and after, simply doesn't exist in the way we understand it. Places where cause and effect break down or reverse. And even in our own minds, we assume that memories come after events that causes pre-ed effects. But what if that's only true within the particular configuration of our own entanglements, our own physical structure? What if there are minds, perhaps not human ones, perhaps not biological ones at all, that experience time backwards or sideways or as a static landscape? There's a concept called the thermal time hypothesis. It was proposed by Kahns and Raleigh. And it says roughly that time arises from the statistical state of a system, that the flow of time depends on the distribution of energy. So if the universe were in a different state, say perfectly ordered with no entropy, there would be no time, nothing would happen. And if that's true, then time is contextual. It depends on the conditions. It's not a universal background, it's a result of particular arrangements. And that to me is profoundly humbling, because it means that time, this thing we build our entire lives around, might not exist independently. That it's not a line we walk along, but a kind of shadow, a projection of something else, something deeper. And if we ever want to truly understand the nature of reality, of everything, then we may have to give up time. We may have to imagine a universe where everything just is, and where our experience of flow, of change, of becoming is just the way consciousness stitches the pieces together. Because consciousness itself might be what brings time into existence. That's another theory, actually, that it's not the universe evolving through time that gives rise to minds, but the mind imposing a temporal order on a timeless structure. That perception creates the illusion of past and future. And if that's the case, if time is something constructed inside awareness, then maybe the real mystery isn't time at all. Maybe the mystery is why we need it, why our minds can't function without it, why we dream in sequence, remember in order, live in story. And there's something almost poetic about that. That time, this thing that feels so fundamental, so rigid, so inescapable, might be nothing more than a scaffolding, a framework, a beautiful fiction that allows us to make sense of a universe that's at its core, not changing at all, just existing, still like a painting, and we're the ones walking through it frame by frame. There's a question that's always bothered me, not in a casual way, but in that deep, persistent kind of way that keeps turning up, even when you're thinking about something else. It's this. Why does time go forward? I mean, really, why is there a direction to time at all? Why do we remember the past but not the future? Why do we grow older, not younger? Why does the tea cool down but never spontaneously heat up in the cup? Because when you dig into the physics, when you really get into the fundamental equations, they don't seem to care. The basic laws, Newton's laws, Maxwell's equations, the Schrödinger equation, they're symmetric in time. You can run them forward or backward and they still work. So then you ask, well, if the laws don't prefer one direction, why does the universe seem to pick a direction? That's where the idea of the arrow of time comes in. And it's tied to entropy. Entropy is a measure of disorder, right? The number of ways a system can be arranged. And the second law of thermodynamics says that in a closed system, entropy tends to increase. So the future is the direction in which things get messier, more mixed up, more disordered. And that gives us a kind of direction, not a fundamental one in the equations, but a statistical one, a kind of likelihood. So for example, if you drop an egg, it breaks, right? The yolk and white spill out, mixed with the shell. That's a high entropy state. But the reverse, All those fragments leaping back together, reconstructing into a whole egg. It's not impossible, technically. It's just staggeringly improbable. There are vastly more ways for an egg to be broken than there are for it to be whole. So what we call the arrow of time is in that sense the direction in which entropy increases. But here's the thing that gets under your skin. It doesn't explain time, it just describes it. Entropy gives us a kind of gradient, a slope, but it doesn't tell us why the universe started off so ordered in the first place. Because for entropy to increase, it has to start low. And that's the mystery. Why was the early universe so pristine? Why was it in such an extraordinarily low entropy state? Because if you look at the universe now, stars, galaxies, radiation, dust, it's chaotic, it's noisy, it's full of heat. Entropy is much higher now than it was 13.8 billion years ago. But that means right at the beginning, just after the Big Bang, everything had to be incredibly smooth. And that's not what you'd expect. It's not the most likely state. The most likely state would be a high entropy mess. But instead, we got this vast, smooth, hot soup of particles that later cooled and clumped into galaxies. And that initial smoothness, that's what allows entropy to grow. That's what sets the arrow. So now the question becomes, why was the universe born in such an unlikely state? And that's one of the great open questions. It's one of those questions where cosmology and thermodynamics and even philosophy start to blur together because we don't have a clear answer. Not yet. Some people have suggested that maybe there was some kind of special boundary condition at the Big Bang, that the universe had to start that way, that low entropy was baked in at the beginning. But then you're just shifting the problem, aren't you? You're not explaining the arrow. You're just assuming it. Others think maybe the arrow is local, not global. That if you had a big enough universe or a multiverse, there might be regions where time runs the other way, where entropy decreases, and the people there, if there are people, would remember their past, which is our future. That's a wild thought, that there might be minds looking back at us from the other side of time's mirror. And there's something else, something even more fundamental. It's the idea that the arrow of time might not be a property of the universe at all, but of observers inside it. That it's tied to the way we experience information. Because when we look at the world, we don't see all the micro-weights. We see macro-weights. We don't track every atom. We see eggs and broken eggs. And that means entropy isn't just a property of the system. It's a property of how we describe the system of how we compress information. So maybe time's arrow is subjective. Maybe it's built into our brains, not into the fabric of space. I mean, even the act of remembering memory itself is asymmetric. We remember the past because that's when information gets written down into neurons, into books, into photons bouncing off a surface. But the future, there's no record of it. It hasn't happened yet. Or at least that's what we say. But imagine a being that lived outside of time, outside of entropy. What would they see? They wouldn't see a flowing river. They'd see the whole thing at once. The egg falling, the egg breaking, the tea cooling, the stars dying, all as a single structure. Timeless, fixed. And the arrow, this thing we cling to, would vanish. It wouldn't be needed. There's an analogy I like. It's crude, but helpful. Think of a film reel. The movie exists, all of it, on the strip of celluloid. Every frame is there, laid out in sequence. But when you watch the film, the projector pulls the frames one at a time. You see motion, you feel time passing, but the reel doesn't change. It just sits there. So maybe the universe is like that. Maybe time is the illusion of the projector and the entropy increase. Maybe that's the way the projector moves. It only goes forward, not back. And this connects, I think, to something deeper, something about cause and effect. Because we say the past causes the future. The match lights the candle. The sun warms the earth. But in the equations, especially in quantum mechanics, the direction of causality is not always obvious. Some interpretations even allow retrocausality, where the future influences the past. Not in a time travel way, not in a science fiction way, but in a statistical way, a kind of mutual constraint. So maybe causality and entropy and time, maybe they're all part of the same phenomenon, not separate things, but different faces of one underlying structure. And then there's black holes. Always the black holes, because when you think about entropy, they push it to the limit. The entropy of a black hole is proportional to the area of its event horizon, not its volume. That's Bekenstein and Hawking. And what that suggests is that the information in a region of space might be encoded on its boundary. That's the holographic principle. And if that's true, if the three-dimensional world we see is just a kind of projection from a two-dimensional surface, then maybe time itself is holographic too. Maybe the arrow isn't flowing inside the volume, but across the surface. The